Okay, so recap, the instructions we know are no-op, or nope, nope. Push and pop, call and return for functions, move, and we don't really need to know about LEA or LEA. Add and subtraction, we know about jump, we don't need to concern ourselves with JCC. We know about compare, we don't need to concern ourselves with test. And yes, we have and, or, XOR, and not. Okay, that's great. So, the next one to look at is called shift, and you can shift to the left and shift to the right. You want to know what shifting is? What are we moving?
Commands.
It depends.
It's kind of correct. Kind of correct.
That's just my go-to answer.
It depends.
Yeah.
After this course, it'll change, but we haven't gotten to what the second answer always is. We'll get to that.
Where is it? There's a
Oh yes. Oh yes, we'll get to it.
Can't be two answers at always.
Yeah, there is. Yeah, there are. Whatever. English.
English. Always this or always this.
English.
No.
All right. So let's pretend we have a number called 0101. That's 5. All right. So if we're going to shift it, let's put some zeros in front of it. Let's shift it 2 to the left. You ready for this? I just realized I'm not recording my board.
Aww.
I shifted to the left 2. What did I do to the number?
You changed it.
You made it bigger.
Made it bigger. By how much?
Some sort of power of 2.
Yes. If you're multiplying by a power of 2, you can just shift the bits. Anyone want to take a guess which one's faster, shifting or multiplying?
Shifted.
Yes. All right. What if I shift right by 2? Well, then, what's the number?
If we're doing the same number, it's 5.
Yeah, it goes back to. Oh yeah, these lines are perfectly understandable.
It's like a flowing river.
Yeah, exactly. Oh, nice. I like it. Has a little bend. Okay, anyways.
It has a whole bit.
All right, so these are shift instructions. These are actually pretty important, and if you have to read x86, you're going to see them a lot. Although immediately it may not seem why, but we should at least pretend to understand why, or at least play with them. Let's do it that way. So what do we have here? We have a shift.assembly. By the way, I'm inside of our class code assembly 09 shift. And let's see what this thing looks like. A equals 64, B equals 512, and C equals 4.
Nice.
Sounds like we're doing some multiplication and division here, but let's take a look.
Can you open it back up in G then?
Yes, I can. And I will.
I shall.
You wanted big mode, don't you? Just so I could hear it. All right. So main, we set up the stack. We get a value. Well, what's a? 40 in hex. What's that in decimal? 64, yes.
Oops.
We push A, or we save the value of A. We push the value for printf. I know that looks funny that we're doing it twice, but that's what we're doing. Push to print A's value. So up here we're going to have A equals something. Call printf, and then we're going to pop twice, and then we're going to pop EAX. Okay, hold on a second here. This might have been a little confusing. Normally when you do printf, you see you just push the two things you're passing, call printf, and then decrement. Notice I pushed EAX and then popped it. What that did is I saved, bless you, I saved EAX on the stack for myself, let printf do whatever it wanted to with EAX, and then I restored EAX down here. So I used the stack, and pushing and popping is a simple way in order to save values onto the stack so you can use them later. Very simple way to go about it. All right, now let's save the value of A again. And let's shift left A by 3. So that makes A equals A times 8, or A upshifted by 3. In C, you might see this syntax. That's what shifting is. And then we'll go ahead and push it back, or set it up on the printf, push AEX, which is value B, call B, print B, pop the stack, and then get A's value back because we saved it at the beginning. So showing you a different way to save values. And then lastly, we're not even going to try and save EAX because this is the end of our program. We're going to shift right EAX by 4. So this is, well, that's not B, that's actually A because we restored it. Divided by 16, which we're now going to call the value of C, and then print off C, and then fix up our print statement, and then exit cleanly afterwards. So, take 64, shift it up by 3, print it, and then take 64 down, shift it by 4, and print it. Okay. How are we doing? Hopefully that was actually a bit of a review, because shifting hopefully is not that complicated. You okay, Jordan? I mean,
I'm never okay.
you're never okay. I meant to ask, does this make sense to you, Jordan?
Nothing ever makes sense.
Never. Are you a nihilist?
Could be.
Could,
Not confirmed, but
It
not denied.
depends.
or are you a nihilist about being a nihilist? What would that mean?
I mean, you'll have to pay for the Louis box to find out.
I'm not giving you any money.
Okay.
The money only flows in one direction in this course. To me. Actually, it goes to the university.
I don't deserve any money anyway.
You don't need money?
I don't deserve it.
Well, that's at least Christian, okay?
But unrealistic.
No,
Huh?
that's realistic.
Okay.
So we got shift left, shift right, and next comes multiplication and division. Everyone ready for multiplication and division?
The new way. Yeah, the new one.
The new, oh yeah.
Thank you. Okay, I was like,
Oh.
I really don't want to explain it, but
Oh.
like if I have to, I'll try.
Anyone? Yeah. Hey, we haven't got anyone that had to do the new math or the dumb math.
Don't get it.
What's wrong with multiplication, Louise?
There's a new way. Yeah.
Why you guys keep training?
Yeah, don't worry.
changing
It's like
it?
the Common Core. Like, you have to draw pictures, illustrate.
Yeah, because apparently using numbers is hard. All right. So we're going to print off A times B equals something. 40 is 64, and 2 is 2. Let's get the value of A, get the value of B. We multiply basically EAX equals EAX times ECX. We push it on the stack. We print a format up there called printf, and we're done. Hey, look, that's a simple program, right? Yes.
Right?
Right.
It is. Never knew this was a curveball or anything, right?
No, that's all it does.
Awesome.
Isn't it amazing how quickly this compiles and runs? Isn't that nice?
Yeah.
Yeah.
Oh no.
Well, I mean, you notice that the
Fast it
assembly simply compiles really fast,
Uh-huh.
and it runs really quickly.
Yeah.
I mean, have you ever tried compiling a Java program and then running it?
You.
Yeah, exactly. It goes whoa, 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 whoa.
Got it.
What are we doing again? Yeah.
Well, like, stop telling me what to do. I'll do it on my own time.
Yeah, exactly. This one, there it is. All right. Well, that was easy, hopefully. Oh, next comes division. Oh, division. All right.
That's
Five.
easy.
What's that?
That's easy.
Yeah, yeah. It's not that, I mean, if you think about it, there's a reason for it. Because when you multiply, you have one answer. When you divide, you really have two answers. And we're doing integer division. So you have the answer to the divide and the remainder. So you have two answers whenever you do a divide. So it's a little different. And here we go. So I'm going to have a divided by b equals this, comma, remainder is that. All right? So I'm going to have 64 divided by 3. That way we have a remainder. Set up the stack. We clear the dividend. The EDX is going to have the dividend. We load EAX and ECX. Then we tell it to do the divide. Wow, this is kind of confusing. But it's going to take this instruction, takes whatever's in ECX, divides it by, takes whatever's in EAX, divides it by whatever parameter you put here, which in this case was ECX. Wow, that's confusing and dumb, but yes, that is how divide works. You must set up EAX properly before you call divide. What's that?
Say that again.
So, notice the state before the divide. We zero out EDX, so EDX is 0. We load in A to EAX, and then we load in B into ECX. So when we call divide is going to do EAX equals EAX divided by whatever the parameter to divide is. In this case, it's ECX. So it's going to do EAX equals or actually, I shouldn't say that. It says EDX. Whew, that was bad. Or hold on. EDX will have the remainder. Let me rephrase that one more time because I always get this mixed up. What this divide instruction says is that EAX is going to be EAX divided by this parameter, ECX. The remainder will be stored in EDX. So notice that we push the remainder, push the result, and then we print it. So when you do a division, the results are going to be in 2 separate registers, and you're not allowed to specify which those 2 registers are because x86 has decided that the result is in EAX and the remainder is in EDX. If you try and put something useful in there, you will be sad.
Okay.
Yes?
So you have to do the moves in that particular order to get it to work like that? Or
The order of the moves don't matter, but those values need to be there before you call divide. I could rearrange the moves, but they have to happen before the divide.
Okay. So what does it divide by? Which thing does
So
it
it's going to take EAX,
EAX.
which is 64,
Mm-hmm.
and it's going to divide that by what you pass to divide, which in this case is ECX.
Oh, you
830.
pass it when you run divide.
Yes.
Okay, that's what I was trying to ask. Okay, so I didn't know if you need to like put it in my register. Now.
And then the answer is in EAX, and the remainder, is in EDX. But you have to zero out EDX first, otherwise it's just going to increment EDX by what the remainder is.
Okay, so this is.
Why? Don't ask me. That's what they did.
Okay.
So this is modular division with a remainder? Or is
Yes, because you're doing integer division.
Okay.
You're not doing floating point division. We'll get to floating point. Don't worry.
So
We
if
might
you
get to
wanted
it today.
to do modulus.
Oh boy!
If you want to do modulus, you could literally just do the same thing and just get
The remainder. Yeah, so very important. Note that dividing and modulus is the same exact operation, the same instruction. It's just which result are you getting? Are you getting EDX or are you getting EAX? That's the only difference. Well, that was a lot of fun. Any other questions about divide? Kind of confusing, isn't it?
Yeah.
Yeah. Welcome to x86.
One question: when you do your print word, how does it know which one to print out? So how do you know you're
Print
printing
word.
out? So like you're going to say what A's value is. How do you know if it's going to print the remainder or the
because
dividend?
it's the stack.
So
I said the order.
So remember how printf works. Wherever there's a %d, that's where it will present an integer that's next. That's the
And
next
then stack.
parameter. That's the next parameter to the printf function. The next parameter on the printf function is on the stack.
Okay.
So by pushing EAX, notice we push EAX last.
Okay.
Last. So that'll be the first parameter. EDX we push next to last.
Okay.
So that'll be the second parameter.
So if you did another %d, would it do the remainder?
Right, and we could. Well, no, that's what we did. We have % for the
you
result.
did have it on there. Okay.
And
sorry,
another
I'm just
% for the remainder. Yeah.
Not paying attention. All right.
These things happen in life.
Yeah. I'm getting off.
Any other questions? All right. Well, that's great. All right, signed multiply. We're not going to look into this too much. Just use imult the way we're doing. But notice that we can do all sorts of weird multiplication, and we can do multiplication with memory addresses or data that's inside of memory addresses if we really want to. I recommend against it. It just gets confusing. Same thing with divide. Ooh, that's the end of that, or so you thought.
But wait, there's more.
But wait, there's more. We do need to do floating.
Yay.
Okay.
I'm gonna learn to
Now,
float.
Way to make
I gotta learn to float.
okay.
Oh,
All right. So we're going to get to floating soon. I'm going to show you, but keep in mind the most important thing to remember about floating point when it comes to assembly, including the guy back there who's looking at their phone, the most important thing to understand about floating is that they are completely separate registers, completely separate circuitry, completely separate instructions. It's almost like a completely separate processor. In fact, it is. Originally, it was a separate processor that goes next to your CPU, and then they just integrated it. So this is going to be really weird because it's like everything is just different because it's like it wants to be that way. All right. So I first set a value to 2.0. Hey, look at that. I create pi because who doesn't like pi? Single sum. A floating point is single precision. I haven't got to that, but we're just going to only work with 4-byte floats for the time being, just to make our lives simpler. User input, just so I can show you how you can get input from the user and put that into a double. And then a single multiplication, which is going to multiply our sum times the user input. Let me show you what this does. Pi times a, we set a equal to 2, so this makes some sense. And we'll go on to put in 3.5, and pi plus a times input, which is 3.5, equals that value. All right? All right. So, how do we do this? Well, before you do any type of floating point operations, call f init to clear all your registers, otherwise sadness will occur.
what happens if you count?
Then you'll have random garbage. You may have random garbage in your floating point operations, including what's a result of a previous add or multiplication, which could change the values of different registers and your different operations to do different things. In other words, the answer is undefined. Float, load, double, or D word. We put pi on the stack for float, the float stack. We put a value on the stack as well. We add the two, which by the way pushes the result back on the stack. Okay, everyone got that? And then we store out the result back to where single sum is. Notice that single sum is right here. So, when this instruction finishes, we're going to take these two values, the sum of them will be right here. Then we reserve stack for a double on the stack. Why are we doing this? Because when you call printf, it expects a double. So, and a double is 8 bytes, not 4. We're only dealing with 4-byte floats because if you try and do double float arithmetic inside of x86, it is just flat out super annoying. But when you call printf, it needs to have a double. So we need to convert our 4-byte float into an 8-byte double float. We're going to go ahead and move the address of our float. Notice that single sum is the address to up here. Then we're going to do a floating double load, of where it is. And then we're going to put a Q word onto the stack. Because notice that this is loading into the floating point register stack. This loads into our internal, our regular stack. Yeah, this is confusing. I know. Again, just think of it as the floating point is completely separate. This loads it into our regular stack. Notice it's a quad word, making it 8 bytes. Then we can load the sum format, which is printing out A's value, call printf, and then we decrement by 12. Why do we decrement by 12? Because this was 8 bytes, and this pointer to sum format was another 4 bytes, which equals 12 bytes. Everybody got this?
Kinda. What is
Suppose what's the full name for FSTP?
I cannot remember. Float, store, something, pointer, something.
Unfortunate. Okay.
Floating, single precision, I don't know. STFP? Let's find out. What was it? FSTP, x86? Store floating point value. Yeah, store floating point value. Sounds great. So that'll print it out. Now we can push what's called user input to scanf. And user input, scanf, and to scan format and scanf. Let me show you what these are real quick. So user input is another 4 bytes right here, and scanf is passing %f. For those of you who haven't used scanf before, doing %f tells scanf to take a 4-byte float from input and write it to the 4 bytes that you pass into it, which is going to be right here. So this is telling scanf to read a float from the user and store it where user input is. And I'll go down here just to show you, because you push user input, which is the address of where you want the float to be stored. You have scan format, which tells scanf what to parse, which in this case is a %f, aka a float. Then you call scanf, and then you decrement the stack 8 bytes because you just pushed twice. So that gets a value from the user and stores it inside of user input. We reinitialize the floating. By the way, this was not needed at this point, but I'm putting it in here for emphasis because as long as you do it for your assignments, you will not have problems. All right, get single sum back from the stack, get user input, do the multiplication, and then store it back out in the single mult. Notice that single mult was right here, so we're storing the result at these 4 bytes. And then what we do next is basically do the same thing we did earlier to print out the floating answer, except for, of course, we're calling single mult. We do the conversion, and then we call it the mult format, call printf, and then exit cleanly. So let's go ahead and do that again. Let's do that again. And what number do y'all want?
10.5.
Oh, I can't go backwards? Ooh, that's bad. 10.5. Okay.
Neat.
All right. Everyone got this? Because even though I've given you a giant project, I think we're finally going to be done with assembly. Yeah, it's about time. And that was the end of the presentation. Great. And yeah, I'm going to be done. This is